Okay, let's take a look at exponents. Right? I'm a big fan of using variables to help us see formulas. Right? So if we have this expression, a to the n, right, that's how we read it, a to the n, or nth power, whatever those numbers are. That means this big number at the bottom is the base. I'm multiplying it by itself this many times. However large the number n is, that's the number of times I'm going to multiply a times itself. Right. Now a quick notation note, you see this dot 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 at the bottom here, that's like in any English sentence or paragraph, dot 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 is the ellipsis point saying it keeps on going. We use that a lot in mathematics. Notice that's at the bottom where these dots are kind of in the middle. If I write something like 8.7, that's not the same as 8.7. This is the decimal point where I have 8 and then 7 tenths. Right, separating the ones place from the tenths place. This dot that's in the middle means multiplied. Right, when we're dealing with algebra, we often use x as a variable, so we don't like using the x to mean multiplication. If you're typing it on a keyboard where you don't have these fancy symbols, most often use Shift 8 to mean times. Right, so that asterisk means times. And if I want to show an exponent, I can't make that really high, so I would use, oops, here it is, 8 to the 7th, or for the example I have here, a raised to the n. So that's Shift 6. This little character here means raised to that power. So in this case, 8 is the base, and 7 is my exponent. Right? Whereas this means 8 plus 8 plus 8 7 times. This means 8 times 8 times 8 7 times. So let's take a look at that with some real numbers. Let's say I have 2 to the 5th power. We saw that in one of the previous videos. And I think there was a typo in the answer key. But we're writing out 2 times itself this many times. Now, multiplication is associative. So I can go in order. 2 times 2 is 4. And 4 times 2 is 8. And 8 times 2 is 16. And 16 and 16 is 32. And there's my answer. Or I can say 2 times 2 is 4. And this 2 times 2 is 4. Right? Just like any time we're simplifying an expression, I'm going to bring down the parts that I've computed and bring down the rest of the expression as well. So now I can do 4 times 4, come on, 4 times 4 is 16, and double 16, I get 32. And if I have to do that by hand, if I don't have it memorized, 2 times 6 is 12, 2 times 1 is 2, 2 plus 1 is 3. So there's my 32. Or I could say, let me switch colors so I can fit this all on the same page here. 1, 2, 3, 4, 5. 2 times 2 is 4. I already know that, so I'm just going to double 4 and jump straight to all of these together, make 8. And then lump these two together. 2 times 2 is 4. And then maybe I don't have 16 and 16 memorized. I'm either multiplying by 2 or adding up 16 plus 16. 6 and 6 is 12. There's 32. But maybe I do have 8 times 4 memorized. Right? That's two one-digit numbers. 8 times 4 is 32. There we go. Right? So this is illustrating something about how exponents work. Here I have 3 2's being multiplied, so that's 2 to the third. And here I have 2 2's being multiplied, so that's 2 to the second power. Right? So this is the same base, I've just kind of split that 5 up into 3 plus 2. Right? I've got 1 2 here, and another 2 here, that's a crooked one. And another 2 here, another 2 here, another 2 here. I've got 1, 2, 3, 4, 5 2's. I could split that up 2 and 2. 2 plus 2 plus 1 gave me the total of 5. Or I could split it up into 2 pieces. 3 plus 2 gets me the total of 5. These exponents are just telling me how many of that base I have as it's being multiplied. So in general, if we go back to our a's here, if both of these have a base of a, I'm just multiplying a whole bunch of a's and then a whole bunch more. My total is going to be that sum. Right? So 2 to the third power times 2 to the second power, that's 2 to the 3 plus 2, 2 to the fifth power. And the same thing works for division. Let's say I have a bunch of 2's that I'm dividing by a few 2's. Well, 1, 2, 3, 4, 5 2's up there. 1, 2, 3 2's down here. Well, each time this 2 is showing up in the denominator, I can cancel it, right? 2 divided by 2 is 1. 2 divided by 2 is 1. 2 divided by 2 is 1. Right? And 1 times anything is that thing. So what do I have left? I have 2 2's left. 2 times 2 is 4. In other words, 3 of these 2's are canceling. So how many do I have left? Well, I had 5. 3 disappeared. So I'm getting rid of 3 from that original 5. I have 2 2's left. So that's my second formula here. When I'm dividing, that means I'm going to knock off however many m's I'm dividing by. And we could see that 2 to the fifth, that's 32. 2 to the third, that's 8. 32 divided by 8 is 4. Right? 2 times 2 is 4. So it checks out whether the base is 2 or anything else, as long as these have the same base. Let's investigate this a little bit further here. Let's say instead of 32 divided by 8, I have 32 divided by 16. So how many of those cancel? All but one of them. I only have 1, 2 left. If I wrote that out in the exponent version, 2 to the fifth divided by 2 to the fourth, I'm going to subtract 4 from 5. 5 minus 4 is 1. Right? 2 to the 1th power is 2. This 1 is telling me how many 2's I have. Well, let's move on to the one we're most interested in here. What if I have 32 divided by 32? Right? We already know anything divided by itself is 1. So 32 over 32, there, 1, 2, 3, 4, 5, 32, 2 to the 5th power. If we show my canceling here, all the 2's cancel, right? Just like 32 divided by 32 cancels, that gives me the identity of 1, right? Think of division. 32 divided by 16 is 2 because 16 times 2 gets me 32, right? That's how division and multiplication relate to each other. If A divided by B equals C, then A equals C times B, right? Um, that's one way we do any kind of division problem. So 30 divided by 32 is 1 because 1 times 32 gets me 32. Well, if I use the exponent rule I just showed to you, 2 to the 5th divided by 2 to the 5th, that's, that's 2 to the numerator exponent minus denominator exponent. 5 minus 5 is 0. I don't have any 2's left. I just have that identity. We can look at this in one more way here. Let's look at the number 28. Right? Well, 28 is equal to 1 times 28. Right? If I'm trying to factor 28, we'll get into factoring more later in the semester, the most straightforward, basic, simplistic way is to say, well, 1 times that number gets us the number. Right? But that's not very useful. Let's think of something other than 1 we can multiply by something else to get 28. So 1 is still there. 28 is an even number, so I could say 2 times 14. And 2 is a prime number. The only way to get 2 is 1 times 2. So let's look at the 14. 14 is not prime. 14 is 2 times 7. And 2 times 7 is 14, so I can replace that 14 with 2 times 7. So 1, that's just the identity. 2, that's a prime number. 2, that's a prime number. And then 7. Also a prime number. There's no pair of whole numbers other than 1 and 7 that you can multiply to get 7. Definition of a prime number. All right, now, sometimes that same factor will show up a bunch of times and it's tedious to write it out. Right, if I'm factoring 32, that's 2 times 16. 16, that's 2 times 8. 8, that's 2 times 4. 4, that's 2 times 2. I don't want to have to count all of those 2's. That's the point of exponents. Now, exponents can be any real number. We'll get into that in later math classes. Historically, and for now, whole number exponents are just indices to show repeated multiplication. Right? So that 1 is still there, right? 1 times 32 is 32. 1 times 2 to the 5th is 32. But instead of writing a whole bunch of 2's, I can just write a single 2 and then put that 5. Same thing over here. I have a 1. How many 2's do I have? I have 2 2's. How many 7's do I have? I have 1 7. Right? That's the idea, that to the 1th power means I have one of those. But sometimes when we're looking at the factorization, we're interested in all the possible prime factors. So 1 is not technically a prime. 1's the identity, it's special. The lowest prime number is 2, so I have 2 of those. The next whole number is 3. 3 is also prime. The next whole number after 3 is 4. 4 is not prime, that's 2 times 2. After 4 comes 5. 5 is prime. Then 6. 6 is 2 times 3, so that's not prime. Then 7. Then 8, that's 2 times 2 times 2. Then 9, that's 3 times 3. Then 10, that's 2 times 5. Then 11. Right, we can go through and list all the prime numbers. But if I multiply all those prime numbers, I'm not going to get 28. I have to use 2 twice I have to use 7 once, and I don't use 3 at all. I don't have any 3s, I don't have any 5s, I don't have any 11s or 13s or 15s. Right? If I take 2 multiplied by 2, I don't get 28. But if I take that 4 and then I multiply by 7, I get 28. If I multiply that 4 by 3, that's not going to get me to 28. I have to undo that by then dividing by 3 so that the 3 disappears. Multiply by 5. No, that's not going to get me to 28. Get rid of that 5. Multiply by 7. Keep the 7. And so on, right? 1 minus 1 is 0. I don't have any 5s. I don't have any 3s. But I'm not multiplying by 3 or by 0. As soon as you multiply by 0, you get 0. That's not getting me to 28. That wiped out everything I had before. So that's showing, again, that anything to the 0 power is 1. That 0 power is saying this has no effect on my product, just like the identity has no effect on my product. 7 does have an effect. 2 has double effect. 2 times 2, that's 4. 1 times 4 times 1 times 1, I'm at 4. 4 times 7, I'm at 28. Times 1 times 1 times 1. I have an infinite number of 1s here. They don't really matter, right? The 1s don't have an effect when you multiply. So 4 times 7, that's my 28. Right? Now we're not going to write this out really ever. It's just showing how that 0 exponent does have a use in this amongst a few other contexts. The 0 means I don't have any of that base as a factor, so that just gives me 1 as a factor, the identity. 1 tells me I do have one of those bases as a factor. 2 tells me I have 2 of them. 5 tells me I have 5 of them showing up as factors in my overall product, and so on. So there's a more thorough explanation of 1 and 0 as exponents, and hopefully that will be useful to you moving forward.